Hi there, this is session 20 of programming from the very basics using Python. In this session, we will learn how to use lists in Python and various operations you can perform on them. We'll talk about list methods and various functions and also built-in operators that apply to list. So a list is a very commonly used data structure in Python. It's a very commonly used collection to store data in an ordered manner, and you can manipulate it with a lot of interesting algorithms and also various functions. Now, how do you create a list here? A list can be created literally using the syntax. First, I'll call this a little notation where you can create a list by using square brackets with comma separated items inside them. Forgot to mention, when I talked about the previous session, when I talked about tuple, I gave all the examples where I made the tuple look very homogeneous. But I should tell you, both tuple and list are both heterogeneous collections, which means that you can have items that are not just numbers, but it can be strings or another list or another tuple and so on. We will talk about more complex data structures by using list, tuples, dictionaries, and sets together in one of the sessions where I will tell you how we can create structured data using these collections once you know them. So for now, for simplicity, I'm just creating lists with numbers in here. You can actually create a list of strings, list of tuples, list of any arbitrary objects, right? So this is a little notation of a list. And as you can see there, I can see here, you can type A and type of A will show you that it's a list. Well, we already learned this in the earlier sessions. This is just a recap to it. Now, you can also create a list using the constructor expression, just like we did with the tuple. To construct a list, but I could say A is equal to create a new list from any iterable object. It can be a range of 10, for example. And when you try to print A, it generates a list of all numbers from 0 to 9. You can pass any iterable object. Can be a string, can be another tuple, can be anything that you can iterate over using a for loop. Now, the last form of creating a list is, as you might have guessed, is list comprehension. Now, you can create a list by using a comprehension expression. And the way you do that is for tuple, you use a tuple constructor, and inside that you use an expression, right? But for a list, you can do it in a much simpler way. You can just use square bracket here and then use v into v for v in range of 10. And when you try to print print A, that is, sorry, you will just see that you have a list which is nothing but squares of all numbers starting from 0 to 10. Square of 0, square of 1, 2, 3, 4, 5, all the way till 9. So it's the same like we saw with the session where I talked about tuple, when I constructed a tuple using tuple comprehension. All the comprehension semantics that you learned with a tuple is applicable to a list. If you want to apply a filter, you can also apply a filter here. Maybe I want to get a square of all numbers which are odd numbers, right? Or not maybe odd number. All numbers that are divisible by 5. But I'm just trying to think something that can be done with range. It's a little difficult. But I'll do one thing. I'll just create a one list here with numbers which are quite random. And then I want to extract all those numbers which are divisible by 3. If you want to do that, you can just use a comprehension where I can say v for v in A if v percentage 3 equals 0. You can see I'm using an if clause here in the comprehension. And what does it do? Well, while this for construct here within this comprehension iterates over A, it tries to take A, I try to check the first value of A, that is, into V, and checks if 44 is divisible by 3. If it is divisible, it will store that in the list. Else, it will ignore it, go to the next one. So it keeps doing all the way till the end and extracts only those numbers which are divisible by 3. When you run this, you can see that you have a very filtered out collection of numbers, a filtered out list based on what you passed here. So you can apply comprehensions just like how you did for a tuple, just that the syntax is you use square bracket and you put the comprehension expression. Either it could be a mapping or a filter comprehension as you want. So these are the primary ways you can construct a list. Now, a list is merely a mutable equivalent of a tuple, which means that it borrows all the features of a tuple, every single feature. You can concatenate a list, you can repeat a list, you can also invoke methods like index and count, which I talked about when I talked about tuple. And all the different operations related to the tuple can be done with the list. In fact, in many expressions in Python, where it doesn't explicitly check for type, that's how it is in a lot of Python code. If an expression is expecting a tuple as one of its arguments, you can pass a list instead, and it is very likely going to work because it doesn't. A list can have all the features that a tuple has, and as long as you don't specifically check whether it's a list or a tuple, you can perform all the tuple operations on it, and it still works. But a list being a mutable object has much more features, much more functionality that allows mutation of values inside them. I would say the list is the first mutable object in a series of built-in data types that I talked about so far, right? So let's talk about all this mutability in a while now. First, let me just quickly cover all these things across so that you know for sure that all these things which I showed you with the tuple works for a list. For example, concatenation, I guess we should be doing it. I'll say B is equal to, let's try something else. And I can say C is equal to A plus B, sorry, E plus B, and then put in C. As you can see, this is concatenation. You can also perform repetition of a list. I could write maybe D is equal to A into 5, and you can print D, and D is nothing but the contents of A repeated 5 times. And this is called as repetition operation. As we all know, these are all common sequence operations supported by all collections that are categorized as sequences in Python. So what is repetition? And you can also do all these element access of a list by using the subscript operator. So you could actually do that here, like say A of 0, A of -1, get individual items, either at the beginning or at the end, or any valid indices which are part of that list. You can also do things like, say, slicing operation. Well, to do slicing and all that, I'll create a list which is slightly larger, like I did before. I'll copy this one. I should make it even more larger. Let's do that. I'll just keep this in the same cell for now. Okay, I'll create a new cell. Let's avoid more of confusion. I'll just say A is equal to this time and copy this and add a few more numbers inside it. Maybe 45, 31, 20. I'll add 18 here. Trying to make it as random as I can. So just going across and putting numbers there. So let's try 48 and maybe 54. Yeah, sizable enough. I got large enough numbers which are sort of random. Looks quite random to me. And if you probably try to access elements, you can access via slices too, where you can say print A of :4 to get the first 4 items of this particular list. Creates a new list. This creates a new list, which is a slice of an existing list. That's what all the slicing operators do, right? You can also use things like, say, A of -4 : if you want to get the last 4 items of a list, last 4 items, which you can see here. You're going to get this. You can try running it now. You can see that very well. You could see it starts off from 88, 20, 18, and 99. You can, as usual, get slices with step values. I want to get every 3rd element from this list. For this time, I can say : 3. You get the first item, then skips the 2nd, 3rd technically is index 0, index 1, index 2. Now we have index 3 available here, 56. 4, 5, 6 indexes available, 77. Then 6, 7, 8, and 9th index available. That's here. And after that, you go to indices and there's nothing more. So only this is what you have at the final result. So you can apply all kinds of slicing operations on a list and you can actually get slices based on your requirement. So this is pretty much all the things that we did with a tuple that's applicable to a list. But what else can you do? Well, a list is a mutable object. What does it mean? You cannot just access items from a list. You can also modify them. You can change them. Let me show you an example. Let's take this A itself. Let's say I want to change the first value of this list. Or let's take some arbitrary index. Let's try to use this index, which is 0, 1, 2, 3rd index. Let's assume I want to change this 56 to something else. Assuming that I know the index that I want to operate on, I can use A of 3, right? I think it's, 3 is equal to, let's make it a slightly larger number. Let's say 500. I can see that I can modify item of a list. So 56 is now being altered to 500. Not just that, you can also, if you want to remove the last, if you want to, let's say, alter the last item of a list, you could also do that by using A of -1 equals anything. Let's say I could make it like 92, for example, and print A. All valid indices can be used. However, you should not use an index that's beyond the length of the collection. You want to find out the length of any collection? I guess I would have already told you that earlier. You can always use len of A. This works even for a tuple, by the way, right? So you can find out the length of this list. There are 12 elements. So the last index you can technically access when you use the positive indices is 11. So if you try accessing by using A of 11, A of 11 is same as A of -1. I'll put both together. You can access the last item if you know the length is length -1, right? The shorthand is using just negative indices. That's how we get the last item. Last but 1, last but 2. By using -1, -2, -3, you can use negative indices. If you try to access beyond the length of a list, let's say A of 15, for example, it'll still throw an error. You can't even assign it. Some of you might ask, can I say A of 15 is equal to some number? That also will throw an index error. You can only change items within a list as long as you're using the valid index to access them. Only existing items can be changed when you use this kind of an operation. These are called as list item assignment, also called as set item. You're setting an item of a list based on its index, based on the existing valid index, right? It's called as a list item assignment operation. You could also do things like, say, not just modify an existing item. Let's say I want to remove it. Now here, I just copied the whole code, but let me just change it again. If you want to delete an item, if you want to remove an item from a list, there are many ways to remove it, but one of the ways is based on the index. You can use del A of, let's say, 3. And now if you try to print A, you can see that after 48, there was 56. This was the 3rd index. 0, 1, 2, this is the 3rd index. The moment I said del A of 3, and when I try to print A, you can see that after 48, there's 45, there's no 56. The list is shortened in size. You can see the size of the list is reduced a bit. Maybe if you want to print the list earlier and now and also print the length of it, the length is going to change. So I'll say len of A. I'll use a format string this time so it looks more intuitive. I'll use curly braces. Len of A equals curly braces here and close this. I'll repeat this print statement all over again in here. And as you can see when I run this, earlier the length of A returned 12. There are 12 items, but now there's one item being removed, so you have 11. I should now talk about del statement. I thought I'll cover all of these together in simple statements, but it can be a little boring. So I want to show you the real use case and then explain it. Del deletes a reference. What does del do? It deletes a reference. So I can tell you that here. I'll just make it a markdown. The del statement deletes a reference. Now this is very important to know what we mean by that. I didn't say this deletes an item of a list. Sorry about this. There's something on my hand. Yeah, on my table. Sorry. Yeah. So what I do here, when I say del A of 3, the 3 is like a reference to an object again. Each index are like references to objects. So the 56 is being removed, right, with this one thing. But del is not just for deleting items of a list. Del can be used also to delete identifiers, which are actually references to objects. So if at all I do this, let's say right now if I print A, what is there defined in the previous cell is visible now, because I just defined A earlier to represent a list. I could do a modification to the list object, but this A as a reference points to this. If I now try this, if I try to type del A this time, no errors, nothing happened. Del A just worked, no errors. But now, if you try to access A by any means, like say A here, what do you get? Name error. What does it mean? I guess you know you get name error. When do you get name error? You get name error when you try to access an identifier that is not yet being defined. Trying to access a variable that is not yet defined, or trying to call a function that is not defined, will always result in a name error, because you're trying to access an identifier that isn't existing. So what del did here, when I said del A, this could be looking like a detour from the list concept, but it's all good add in place, right? So the moment I said del A is a label referring to an object. What del does, it tears down that label, not the object, the label. A is just torn down. It's like I have a label stuck on an object. Like, so I have a label here, and maybe, what do I find here? Yeah, I have another glasses here, I think. Let me get something else, which is, yeah, my mouse. A good one, my mouse. I have a label stuck on this. It's like a tag on the mouse. Maybe I could write something on the label to say this mouse is mine or whatever it is. So this is a label that represents what this mouse is. So I can tell someone there are many mouses in many mice, I would say. I say mouses, it's actually mice, right? Okay. So I have a couple of mice in my room. Like I have 1, 2, and I have a third one. Okay, there are so many mouse here, right? I got a lot of labels here. I could put one label on this, one label on this, one label on this, and just walk out of the room and ask somebody, get me the mouse that is labeled as A. Maybe I write A on this. That's how these tags represent the object. This is exactly the role of a variable in Python. And what does del do? Del removes this and crumbles it up. Thrown. Discarded off. What happens now? This object loses the reference. This object loses the reference. When this object loses the reference and there are no more labels on this object, this is an unlabeled object. A label, there's no reference to this object. Object like these are candidates of garbage collection. I talked about garbage collection with an example of hotels in Bengaluru, right? I hope you recall that, right? I've seen this happening in many times when in my old office, I remember, we used to have a lot of things on my desk. When I used to work in my old office, a lot of things on my desk. And every now and then people come and clean up their room, clean up everything, clean up all the stuff. Sometimes if they see some things lying around on the room, like say a sheet of paper lying on the room, they think it's just garbage. They take it off. Garbage collected. Next day I come and look at that sheet. It's missing. It's just lying vacant. It's just lying on this table and there's nothing added. Really want to make sure that the sheet is important. I could put a small tag on it and say, don't touch this. So cleaner will say, oh, okay, some tag is on that table. Some tag is on that particular sheet of paper. So let's not touch it. Right? So this is exactly how objects are dealt with by Python. So if you really want an object to be freed from memory, you remove all their references, all references to the objects, you remove them. Some of these references go out automatically based on scope. When I talk about scope, when I talk about functions, I'll talk about scope. That's the right place. Sometimes identifiers have a particular scope. When you call a function, all variables defined inside a function, there's scope to that function by default. Now the function exits, all these variables are disposed of. And what about the objects they refer to? As long as the objects are not being referred to by anyone else, any part of the Python code, I would say, these objects are garbage collected. They're freed. Sometimes you have a global variable which live a very long life. I mean, the scope of a global variable is for the entire program. You exit your program if you want the global variables to be disposed of completely, right? But then if you want to manually dispose of a global variable, therefore reducing a reference to the object it points to and allowing the garbage collector to do its job of cleaning up the object, you could use del to manually delete variables like these. But I use the word variable. Let me tell you, you can delete any identifier in Python using del keyword. Sometimes some of these can look a little dangerous. I'll talk about, I'll give you an example here. This could be a regression again, but nevertheless, it's a good point to mention. If I just say import a module, let's say import time. Time is a built-in module. I just imported it. It's now loaded in memory. What does import do? Reads a module into memory. A module could be a file on disk. This may not be. Let's assume it's a file, right? The file is read into memory, and I told you how modules are loaded. The module file is read, compiled, bytecode is generated in memory, and there's a module object created representing that bytecode, ultimately, right? And all the statements which conform to definitions are all now part of the module object. When it says on time.cTime, this works, right? I'm able to access time, current time. Right now it's showing current time on my machine. So if at all I do this, let's say del cTime or del time.cTime, I don't call it. When I call it, I'm calling the function. I'm not interested in calling the function. The name cTime is a reference to the function. What is cTime? It's a name. That's a name. That's a label to a function. It's a del and I say time.cTime. I do this once. In the entirety of this runtime, henceforth, I cannot do time.cTime whatsoever. Oh well, cTime is removed. Now, some of you who come from other language backgrounds might wonder, oh, can I really do this? Isn't that dangerous? It's a feature. It's like I bought some equipment, or maybe a good example is I bought a bike. The bike has got a lot of features provided by the manufacturer. There are certain things I don't want in the bike. It adds more weight. I strip it off. I strip off all the things I don't need. I remember when I was a small kid, in India, we had this craze of dirt bikes, Indian bikes. I remember the days when we had these less than 100cc bikes, which are like these dirt bikes. The point is, the manufacturers, when they come out of the bike, they put a lot of safety features added in, which adds extra weight to the bike. Some of the people who buy those bikes will remove everything. The mud guard and all the shields and everything is removed. And the only thing that remains is the skeletal tires and the chain and sprocket and the engine perhaps and the handlebar. That's it. So the bike becomes extremely light. And now it can just rev the accelerator and it just goes faster, extremely fast than what it's intended for. So they remove things that they don't need, even from things that we don't create. It came from somebody else, right? We call this as monkey patching. Monkey patching. I'll talk about monkey patching, duck typing, two interesting concepts in Python in a dedicated session. I already have some YouTube videos on that, but I'll be covering that as a part of the session with more examples. There's actually a kind of monkey patching. I just deleted things we don't need, removed it. There could be a valid use case. Maybe you have a module which has some dangerous function which I don't want to use even accidentally. Maybe my program can be, my program is a large program. It could be a big framework which I'm building, which allows some plugins written by others that can use a lot of parts of my program. And my program is loaded a module which has certain dangerous functions. I don't trust the plugin written by somebody else. I don't want that plugin to access that dangerous functions. So sanitize it, remove all these functions off, or all those attributes. I can do that. So del lets you delete any reference. Anything that refers to objects can be deleted, right? So this is what you should know. But del can be used also to remove items of a list by using del list of item. You'll understand in a while that every index of a list is ultimately a reference to other objects. That's how it is even in a tuple. We'll talk about that in some time now. But for now, you should know that you can use del to delete this. You cannot, not only that, you can also delete the module itself. You can say this time is an identifier that refers to a module. I don't need this module in my namespace right now. I don't want to access time anymore. I can say del time. And after that, if you try to say time dot anything, even local time, it's not going to work. It throws name error straight away. Name time is not defined. Does a module get unloaded? Not really. Python maintains something called as a module cache. That's the implementation detail again. Modules once loaded remain in memory. Just that you decided, I'm not interested in the module. So your namespace is clean. The module is there in memory, but you can't access it. That's what it means. Next time you change your mind and you want to access the module, say import time one more time. This time the module is not loaded from scratch. The existing module reference is given to you. That's exactly how Python deals with memory, with modules especially. More about it in the part 2 of modules. I will give you more details about that. Now let's get back. I was talking about list, and I told you how does del play around with a list. Remember, if you say del A, the entire list object is no longer accessible because the reference to it is removed. But you say del A of index, it removes an item from a list. But I don't just want to remove an item. I can do something more interesting with the del keyword. Let's copy this. C and V, right? Okay. I have a list here. Instead of deleting an item, maybe I want to remove the first 5 items of a list. Oh yes, you can do that. 5. The del, when you're using a list as an argument, you can also pass a slice. This entire slice is now stripped out from the existing list. Remember, it doesn't create a new list, right? You can see that. The list originally had about 12 items. The len of A shows that. Now, when I say del A of colon 5, the first 5 items, that is all of these, are removed from the existing list. I can also show you that it does not create a new list because I can also print the ID to prove that. I can just do a ID of A equals here, and ID of A equals gives you this. The IDs are not changed. It's all the same. Maybe we can just trust the last few numbers, right? 78528, 78528. I think if you go cross verify all the numbers, it'll be the same. That means the list is not a new list. It's an existing list with some items removed. So you remove a slice, and all kinds of slice can be used here. So you can also do this. You can also remove the last 5 items if you want to. It's pretty obvious. You have to say del A of -5 colon. We'll remove the last 5 items. But what is interesting, you want to remove every alternate items of a list? Oh yes, you can do that in just one line. This is what gives you superpowers in Python. If you've been doing programming in C or Java or C++ or a couple of those languages, try solving a problem like this. Maybe you have an array of some values, some numbers, and I want to just remove unwanted items from it, like every alternate item. It's one-liner here, but many languages, you have to write a chunk of code to do that. It's not straightforward, right? So you can see that this is how we can remove slices of a list with extreme ease. Therefore, the list is now shrunk in size with only the alternate items, which you can see that it removed 12, retained 34, removed 48, retained 56, removed 45, retained 54, because I used the step value as 2. So you can see what remains are the ones which I did not remove. So del can be used to remove not just an item from a list. You can also use it to remove slices from a list. Now I'm going to talk about some more acrobatics with the slicing operations in on a list. So let's take this existing list now, which I created painfully rather. Took some time to create it. I'm going to reuse it for most of the session. I have a list here. Now, I told you how to change one item in a list, like 56. I did that by using A of 3 equals 500, right? I did that. In my earlier cells, I showed you that you can change one item, and if you print A, you can just see that 56 is replaced with 500. But what if I want to replace 56, 45, 54, 77? I want to replace these 4 items in a list with something else. Guess what? The left-hand side, you can use a slice operation for a list. I want to start from 3. Let's assume 0, 1, 2, 3, 4, 5, 6. So I'll take it as 7. 7 is stop index. Stop index is not inclusive. So I'll say 3 to 7. A of 3 colon 7. Let me provide some numbers like say 2, 6, 5, 4. It's not really random. It doesn't matter. I'll say 3. Okay, never mind. Now try to print A. You can closely observe the values from this part of the list till this part, which is that slice A of 3 colon 7. That's what this slice selected, right? This A of 3 colon 7 selects this part of the list. And I'm using that in the left hand side. When I do that, when I use a slice expression in the left hand side of an assignment, the right hand side, I have to provide an iterable object. Oh, I'm very specific here. An iterable object. You can see this. I didn't pass a list here. What did I pass? Tuple. Comma separate items, make up a tuple. You can pass a list if you want to. Why waste a square bracket? You can just use a tuple here. No problem. There's another use case of a tuple. And now when you see that, you can see those items are replaced with the elements of this iterable. I use the word iterable object. Who knows? Maybe I can just say, I want to replace maybe the first 3 elements, the first 3 items with a range of 10, 20, 2. Print A. Remember, the size of this iterable, how many items this iterable gives you, doesn't matter. It can be larger, it can be smaller. The list will fit it. The list can grow in size or maybe shrink in size. So for example, right now you can see this. I just took 3 items off from this list, but replace them with maybe I guess 5 items. Yes, roughly, yeah, 5 items. You can see that. But maybe I can replace the 5 items with just 2 items. I can also do that. I can just do A of colon 5 equals, I can just give some numbers. Let's say, this time I'll do this. If I can put it funny, I can just say, hi, a string. It works. Oh, remember, when you pass a string like this, a string is an iterable, which means each item of the string is going to become one item of the list, replacing what existed at that slice. So when you try to print A this time, the list now is become sort of heterogeneous because you can see the first character of the string becomes the first item of the list, second character of the string becomes second item of the list. But what was existing earlier, these 5 items are being replaced with these 2 items that you see here. So these are the interesting things you can do with a list if you know how to use slicing, dicing operations. We call slicing, dicing. You can delete slices, maybe first few elements, last few elements, step values, remove elements based on step values. Any part of the slice can be deleted. You can use this slice in the left hand side in the list equals, you need to pass an iterable. Now there's a common problem that many people face is this. Let's say I just want to add one item, just one item. I want to add just one item, replacing 3 to 7. So I say 3 colon 7 will select 1, 2, 3, this third index all the way from here to here, right? I want to replace all these 4 items with just one item. It's very common to put a value here, like say, I want to replace it, let's say 0. Will it work? Let's try. Let me remove all the other parts here for now and try running this. Whoops, it threw an error. You can see that. Type error can only assign an iterable. 0 is a number. A number is not iterable. It's not a collection. It's a single value. What do you do now? Here's a weird hack. I am not very happy about this when I see this kind of a code, but this is what works. You can actually put a 0 and with a comma. And when you do that, you can see it works magically. It worked. A comma made the difference. But you know what? My suggestion, don't do this. Don't do this. Don't do this. Because we human beings are known to make a lot of mistakes. And maybe you did this because you figured out this worked, but somebody else is going to read your code. Might not be carefully obvious. It's not very obvious to that person that there's a comma here. Let's say 3:70 and wonder what's going on. And sometimes maybe he's refactoring code and actually the 0 got removed and I was going to wonder what's going on. So if you want to just remove one item, though this works, I'm going to leave it. I would rather recommend when you have a single item to replace, just put it in square brackets like this. It looks very explicit and readable. Oh, it's a list. Right hand side now is a list. It's very clear. It's staring at you. Square brackets, 0 is inside it, and it works, right? So this does not look very obvious to me, right? Don't assume that Python programmers are wizards who know magic. They are poets who appreciate poetry. They read poem and they like to see that poem with all that beautiful verses in them. So you want to make your code look like that. Just putting ending at the comma doesn't make it look nice. So just put it this way. This is more obvious, more explicit. There's a Zen idiom in Python. Explicit is better than implicit. Don't try to hide things in your code. Make it reveal itself. So people know exactly what this code intends to do without any hidden agenda, let's say, right? So this is something you should know. Anyway, so I told you how you can use these slicing operations on the left-hand side and either, substitute items, replace certain items, delete items. What if I want to insert something? What do you want to insert? I don't want to replace anything. I want to just insert. So this is how we do it. You can actually do this. Let us say that in this given list, between 48 and 56, I want to insert a value 100. Or maybe 2-3 values. Maybe I want to insert, let's say 100, 200, 300. Between 48 and 56. So what is the index where you want to insert? 0, 1, 2. I want to insert at the third index. I want it after 48 at the third index. So the trick is, you can't say a of 3 is equal to 100, 200, 300. This is not what it meant. You know what it did? It added one item at the third index, and that item is a tuple. It added a tuple inside the list. I don't want to add a tuple. I want to add 3 items, 3 different numbers into a list. If I want to do that, I could actually use a slicing operation, but this time it's a little tricky. 3:3. I know it's a little weird. 3:3. If I say 3:4, it'll select one number between 3 to 4. Third index is selected. But if I say 3:3, at that position, a slice gets inserted. Whatever iterable you pass on here, it could be a tuple, it could be a list, it could be a range, it could be string, any iterable would work. And you can see that between 48 and 56, which is retained. See, after 48, there's 56. The 56 is still there. And all the other numbers are still there. 3 values are inserted. Not many people will know about this. Not many people would have exposed this to you. Yeah, these are the hidden nuggets I'm telling you in Python, right? So you can actually insert multiple items at a given index in a list by using a slicing operator like this, use a slice like this, equals, pass on whatever number, how many ever items, it'll work. You can say 100, 200, 300, 400, 500, 600, you can put a lot of numbers. Or if you want to just insert one number, you can just put 100 comma or 100 in square brackets. That's one thing that should tell you. If I just want to insert one item, if you want to insert one item, you have to say a of 3 colon 3 is equal to 100 comma like this. This looks very unintuitive to me. I want to insert one item. I say, I know that I say a of 3 colon 3 equals not just 100, 100 comma. And I told you why the comma is required. Because the moment you put 100 comma, that becomes a tuple of one item. Remember I told you, how do you create tuple of one element? Value, comma, right? That's how it is. Or you have to put this in square brackets. To make things more intuitive, Python provides a helper method to make it easier. Specifically for this, you can rather say a dot insert of at index 3 100. This looks more obvious, better. You can insert one item just by using a dot insert, specify the given index, and you can pass what item you want to insert. The item is inserted, growing the list in size to accommodate that new item in place. The list is now grown by one item extra. Of course, the limitation with insert is that you can't insert more than one items. There is no equivalent of inserting multiple items into a list, right? It's meant for inserting just one item as an index. Some of you might think, what if I want to insert, let's say, multiple items? Let's try this. Let's try maybe 100, 200, and 300. It'll fail because insert just takes two arguments. Index, item. That's it. You pass anything more than two, it's not smart enough to figure it out. There's a limitation. So if you want to insert multiple items, you have to resort back to the slice mechanism, the slicing mechanism, which I think, where was it? Yeah, it's here. Yeah. No, this one. Use this technique. If you want to insert multiple items at a given index. But if you just want to insert one item, you're better off just use the insert method, specifying the index and the item that you want to insert. Some of you might ask, what if I pass this like this? Maybe a list or a tuple as one of the argument. Will it work? It does, but it ends up creating a nested list. You have the third index, which represents another list in its entirety. It's like it's a new compartment added in, right? Which has got 100, 200, 300. All of you are clear, I hope, with this ways of performing operations on a list. Now let's come to other features. Like say, I want to show you something very interesting here. Say A is equal to, and I'm just going to use 10, 20, 30, 40. Just keep it simple. Small list this time. If I try a dot insert of 0, comma, something else, let's say 5. You know what it means? It's inserting in the beginning. It inserts right in the beginning, thereby growing a list to the right, shifting all the elements to the right. So it's added a new item at the index 0. What was existing at index 0 has moved to index 1. What is index 1 has moved to index 2, and so on. The list is grown. Fine. What if I do this? You know the length of the list is 1, 2, 3, 4 items. So the last valid index for a list is 3. Let me prove that to you. If I try to access A of 3, will give me the last item, which is 40. But try accessing even A of 4, it's not going to work. Am I right? It's going to throw an index error. We all know that. Let me copy this cell again. So I try to access beyond the last index. It'll throw an error. It says, oh, this is invalid. Throws an error. Now, what if I do this? I say a dot insert at index 7. 7 is definitely not a valid index for this list. The list has got just 4 items. 7 is way high, way above, way outside this bounds, right? So I say a.insert 7 and say 50. Let's see what happens. Surprising. Some of you might call this, oh, this is a bug. I thought that. And I used to think that. Then it occurred to me that the list is designed like that for a good reason. Sorry for the small interruption. I will just be back with some books to demonstrate this. I've shown this in another video, but I don't have the books with me. I'll just be back. Just one moment, please. All right, so it sort of vanished behind this green screen. My books library is there, and I got some books here. I'm not sure if you can see it on camera, but I have these books with me. Ah, it's a bit heavy to hold it. Let me reduce the books. I'll keep just 3. I have 3 books in front of me. A list is a collection no different than these books. So don't worry about the book's content. These are all very, very old books which I bought long time ago when I was doing things like awk and shell scripting and all that. They're all from Rayleigh publications. Good books though. Very nice ones. Skimmed over all. It's all decades old book. But never mind. So I have these 3 items here. This is index 0 at the bottom. Index 0. Index 1, I think, is the book on awk, I guess. And index 2 is, I guess, it's a corn shell book. Book on corn shell scripting. If I do insert at index 1, you know what it means? These items must move up. These items must move up to make space for another book here. So I know it's holding it in my camera. It's a little challenging. So it's like, these are too heavy. But yeah, I'll just do this. This is how it happens. So it's like, okay, it was like, this is how it is. It's like when I'm inserting a new book, these existing books has to make way. I mean, they move up to make space for this book. You go inside in this place, in this slot. That's where insert works, right? But what if I want to insert not anywhere in here, right? You can see this index 0, index 1, index 2. 2 is the last index, right? 2 is the last index because there are just 3 books here. Index 0, 1, 2. I try to insert at index 7. 7 is way above. I try to insert it here. What happens? It falls. Sorry if you heard a loud thud on the camera. Sorry, on the microphone. Sorry about that. So you can see that. I try to insert on top, but the gravity makes it become the last item. Now where is it now? Is it not an index? Is it at index 7? No, it's at index 3. Yeah. 0, 1, 2, 3. The third index. Earlier there's index 2. Though I try to insert index 7, it falls all the way and becomes the last item of this collection. You can consider a list practically like that, right? It works pretty much like that. This is original. Let me keep this book aside. I'll organize it back. So I told you what a list is. Whenever you think of a list in your mind, just think of books stacked one on top of the other. That's what a list is. Like 10 is below. On that there's 20. On that there's 30. On that there's 40. On there's 50. If you put 70 somewhere on top, it falls and becomes the last item. That's what happens when you do insert. The list grows, right? And this is not an error. This is the intent of how vectors are designed, right? Now there's a shorter way to do this. This doesn't look very obvious to me. It's nobody would want to say, you want to add a new item at the end of a list. You want to find out an index that's beyond the length of a list and then insert it there. You need to know the length of the list for that. That is not practical. The shorthand for adding a new item at the end of a list is what you would call as append. Think of append as a more intuitive term or a name given to insert an item at the end of a list, exactly after the end. So this gives you the same effect. So don't do this. Just for demonstration. Don't use code like this. This in production. This is for learning, right? Don't do this in your production code. But you should note that when you want to insert an item at the end of a list, immediately after the end of a list, you do so with append. Append adds a new item at the end of a list, right? So this is something that you should know about insert and append. Now we'll talk about something about append here. Let's say a is equal to, as usual, let's say a is equal to 10, 20, 30, 40. Okay, and let's use another variable. Let's say b is equal to 50, 60, 70. Now what I want to do is that I want to add all these ingredients of b, that is like 50, 60, 70 must go into a. You want to add 50, 60, 70 as 3 items in a. That means I want to take all the items of b and add them at the end of a. I want to grow this list that is represented as a by 3 items that comes from b. If you want to do that, you try using append method and try to print it. I'll print what is a before and what is a after, so you can see the actual outcome. And as well, you can see that it's added as a single list here. Maybe this is not what you wanted. This may not be what you wanted. You don't want to create another nested list inside. You want to take all the items of an existing collection and extend, use the word, extend the current list with all the items of another list, another collection, or another iterable. I use the word iterable here. You can do that using another method, which is a dot extend of b. So you can see the difference between append and extend. Append is used to just add one item at the end of a list. If that item is another list, the entire list is added as one element, one item at the end. But the moment you use extend, what does it do? It expects an argument, which is an iterable. It iterates over it, gets every item of the iterable, and grows this list, adding those iterables. Therefore, the existing list is extended by the items of b. So this is something that you should know about extend versus append. You also know what insert does. Insert lets you insert an item anywhere in a list, one item anywhere in a list again. Append lets you add to the end of a list. You can't use append to do anything else. It'll add at the end of a list. Think of append as a shorthand or shortcut to insert at the end. That's what it is. Just given it the intuitive name, that's it. Right? So I talked about insert, append, and extend methods that you can use on a list to grow them, right? If at all you want to, let's say, not add elements, you want to remove elements. In order to remove elements, I already told you can use a del keyword, isn't it? Yeah, you can remove elements using del. That's a more convenient way to do that. But there's a problem with del. Maybe the problem statement is, I want to remove an item from a list and I want to store it in another variable. I want to access it through another variable. I want to remove it, but I want to still access it through another variable. So one of the ways you might think of doing that would be a is equal to del a of, let's say, 0. Will this work? Will this work? Well, the VS Code has already highlighted it. So give you a hint that this is not going to work, right? That's a good thing about VS Code. It knows exactly what you're doing and says, this won't work, this won't work. Now try it. Let's try and find out what's the error. It says syntax error. Remember, it's not a runtime error. It's a syntax error. It says invalid syntax. Why is it an invalid syntax? Any guess? If you remember, I told you about statements in Python. And I told you statements are not expressions. What I've done here, I try to use del like an expression. If you use del like an expression in the right hand side, it is going to throw an error because that's invalid grammar altogether. You can't use any of the statement keywords like del. You can't use def, right? You can use if and for as long as they're part of the ternary if expression or comprehension. That's the only place you can use it, but it will not work otherwise, right? So this is a statement. Del is a statement. You can't treat it like an expression. So what do I do? Well, there's a method for it, as you might have guessed. If at all you want to remove an item from a list at a given index, and you want to access that item which is removed for later usage, you could rather use list.pop of index. It's a list.pop of index, and if you try to print what's A this time and what is B, you can see the outcome. The list has one item less. You can see that, oh no, I think I removed the 0th index, by the way. So it removed 10. So whatever index you mention, item at that index is removed. It removed the first item. And now we can see that the list has 3 items, which is only these 3 elements. The first item being removed. But you know what? V can be used for, the variable V can be used to access that item. It returns the item being removed. That's what pop does. Right? So this is what you should know. Pop can be passed with an index, and of course, whatever argument you pass to pop must be a valid index. You cannot go beyond the bounds of a list, right? You can pop the 0th element, the first element, the second element, all of them, right? If you're all one common mistake, what people do is, what if I do a pop of 7? You know, obviously 7 is an invalid index. What do you get? You get a index error. Pop index out of range. Whenever you get a pop index out of range, you're trying to remove an item from a list where it could be empty, very likely, or the index passed for pop, whatever argument you pass to pop, is beyond the bounds of the list. The list is smaller than that, right? So you try to pass an index that's larger than the length of a list, you get this error. Now, pop also takes no argument. You can call pop without an argument. The argument to pop is optional. If you don't pass an argument to pop, by default, it removes the last item of a list. The last item. I'll tell you something very interesting part of a list. From the performance standpoint, on a list, adding an element at the end of a list or popping out the last item of a list has the least performance overhead, which means it can work faster. It's easy to add a new item to a list at the end or remove an item from the end of a list. Coming back to the books here. Let me get back to books. Yes. Couldn't find smaller books than these. All of my books are thick. These are actually thin books. There are even big block books, which is difficult to even hold in my hand. This time I have this list with 3 books. It's a list of books right now, right? When I say a list, just remember books stacked one on top of the other. Or anything, you know, it can be even CD-ROMs if you are into that, music CDs or all that. In my generation, we used to do that, stack them all on top. So it's a book, right? Books it's a stack of books, which is a list of books technically. A list is technically a stack. Can be used as a stack. That's what I mean. It's easy to add a new book on top, like this, as long as I can hold it with my feeble hands. Yeah, you can see that here. It's very easy to add a new book on top without disturbing any books below. None of these books had to be re-indexed. It's easy to add a book on top. Append is cheap, but inserting a book at the beginning is difficult. Inserting a book here is difficult because the entire book is weighing down. If I have like 10 books, forget about holding it in my hand. I can't with my feeble hands. I'm not into that gym kind of a thing. Okay, so I'm a keyboard warrior. So if I have this 10 books Imagine inserting a book at the below. You need to hold these 10 books on top. That means you have to reshuffle all these 10 books to make it like the zeroth book becomes the first book becomes second book third. You have to do that and make space to insert a book here. So insertion can be expensive, especially go towards the beginning. The more towards the beginning, the more effort for reindexing all other limits. Likewise, if you had books like this, if you had these 4 books like this, removing the book from top is least effort. It has least effort to remove a book from top, right? I didn't have to disturb any of the books here. But if I had to remove a book, maybe the second book, which is this one, this book, or remove this book, it's not going to be easy, right? It's not very easy for me at all. It's almost like impossible, but yeah, normally you make space for it and sort of remove it. Let me just keep it below and partially remove it and show it to you. Yeah, what I intend to say is that I'll remove this book. Removing this book means there's a lot of weight of this books on top weighing on this, right? The moment you try to remove this book, all of the books on top has to be reindexed. What was the third book becomes the second book. What was the second book becomes the first book. Oh, actually, it's the other way around. Sorry. What was the third book becomes second book, and what was fourth book becomes the third book. That's how it is, right? So there's a reindexing cost that's involved. So this is the same aspect when it comes to how lists are organized in memory. A list is a vector. It's called a vector. It grows easily in one direction or shrinks in one direction, but the floor remains the same, right? The floor is in one place, but you can add elements stacking on top of each other, remove elements from top easily. And that's what is designed to be used as, right? So many of you who come from other programming language background will have a misconception that it's called a list. So it could be implemented as a linked list. Oh, don't worry about what a linked list means if you're new to programming. Don't worry about that. I'll be covering all these concepts much later. But for now, with those of you who come from programming background, I want to break that misconception that you might have that a list in Python is not a linked list. It is not a linked list. It is a vector. A list in Python is much similar to vectors or array lists in Java, if you come from Java background, or even vectors in C++. That's what the correlation is. It's not like an array in C. No, it's not. An array is homogeneous. You have integer array, which can only hold integers. Floating point array can only hold floating point. What is a list here? It's a high-level data structure. It's not a primitive data type like in C language. It's a very high-level data structure. It's called a vector, right? They should call it a vector, but vector is something that's not used very frequently in programming. So they call it a list of numbers. List. It's a list of numbers that you see here. That looks very commonly used term. They're stuck with it. But the implementation, it's not a linked list, right? So if you don't know what a vector, linked list are in data structures, I will cover them slowly, right? A couple of more sessions. I'll go one layer deep, covering those implementation details. I talk about collections in Python. But for now, these are the things you should know about append and pop. So by using append and pop together, you can implement a stack operation on a list. You can treat a list pretty much like a stack. So if you want to do a stack-like operation, what do? You could do this. You could actually use, start with an empty list. This is how we create an empty list. And then let's say I want to take numbers from a user and keep adding on to a list. For that, I can type while b : equal to int of input of enter number. Disclaimer, this is modern Python, which I'm using. Obviously, I'm using the Valorous assignment. So if you're using very old versions of Python and not the one that I recommended you install, like if you're stuck to Python 3.6 and 3.5 and all that, this may not work. So your code might have to be elaborated more. Okay. So this is for latest versions of Python. I recommend using Python 3.8 or above for this to work, right? So as a v is equal to int of input of enter number. There are too many parentheses here. Oh, I'm not checking the condition for it, am I? Okay, I guess I am not. I need another parenthesis. I'm not sure why it highlighted it. It's fine. I'm gonna wonder what condition am I checking? While loop is supposed to require a condition, right? Well, I can get away with it. I can just type enter number or 0 to stop. You know what happens? If the user inputs 0, v is equal to 0. If 0 is evaluated in Boolean context, it becomes false. So you don't need to check for the condition. You don't have to say greater than 0, not equal to 0. You can drop that. Just use the succinct versions in Python, right? People who come from other languages will think, oh, this is not explicit. No, you don't know Python. That's my argument. Right? All right. So here, I'll just type a dot append of v. So we add elements to v, and I'll also print what is getting added. Now the list is growing. I'll just type a is equal. I think that should be sufficient. You'll see the list growing as you keep adding numbers. Once I'm done, I'm going to apply a pop operation. It's a print popping items. What I'll do this time is very interesting. I'm just going to say while a. Some of you might have habit of telling while len of a is greater than 0. Don't do this. Don't do this in Python. Don't do this. You're trying to make your Python program read like a C program, and that's not what you should use Python for. The reason why you're learning Python is to enjoy and the benefits what Python provides. The Boolean truthiness. Note that. I would have told you that all collections evaluate to true in Boolean context as long as they are not empty. So as long as the list is not empty, this used in a while loop will evaluate to true. So the while loop will run its body where I can actually do this. I can say v is equal to a.pop, pop the last item, and then print pop. I forgot to use a f string here. What v is equal to, and also print a is equal to. See what value I popped out and what is the value of a now, right? Let me run this code. I'm going to give some random numbers: 45, 34, 78, 12, 62. To say I'm done, I'll put 0 here and press enter. You can see first I entered 45, then 34, then 78, then 12. You can see it's getting added at the end of a list. A list is shown sideways here. Sorry. But when you visualize it, you think it vertical, right? 45, 34, 78, 12, 62. Numbers are stacked one on top of the other. You're popping out items. When you call just pop method, what happens? You're removing the last item out. Then the previous item. You can see that? Next time it's popped, 12. The list is shrinking by size, right? You can see that once you popped out 62, the list just has 4 items. I popped out 12, there are 3 items. I popped out 78, there are 2 items. The list is shrinking. Eventually, the list becomes empty. This code, this whole code is what is happening from the while loop. This while loop here, right? This while loop that you see here. While the list is not empty, that's how we read it when you say while a. V is equal to a.pop and say what got popped. Eventually, when the list is empty, the loop completes gracefully because the loop condition is false, right? And this is how you can apply stack-like operations using a list. A stack is a first in, last out, or rather a last in, first out operation. Last item in is a first item out. The realistic example of stack is stacking books one on top of the other, stacking stuff one on top of the other. The last item that is stacked on top is what you get when you try to remove it easily, right? That's what stack is all about. When you have a pile of things kept on one on top of the other, you're actually stacking them. And it's easy to just remove elements in the last in, first out order. Right? That's exactly what a stack operation is. You might ask me in computer science, where is stacking used? Can you guess? One real example I can think of is your browser's, history. You go to a new website, then change your mind. You type, go to the URL, try go to a new website. Click on a link, go to a new site. You keep going to new pages, right? And you can hit on the when you hit on the back button, what is exactly happening? Last in, first out. When you hit on the back button, last page. Hit on the back button, previous page. So you're going to new pages. Each page context is stacked by the browser. So it's using a stack implementation there. So when you're actually hitting the back button, it's going backwards, right? That's one of the realistic use case of stack, which you can see in every day in your browsers. It's used in many other places. Within a programming world, function calls, the state of every function is maintained in frames of stack. So function A has its own state, like it's got its own local variables, but it's calling function B. B creates its own stack frame. And B calls C. C creates its own stack frame. When C is returning, it's unrolling back to B. B returns, unrolls back to A. And A returns, unrolls back to main. Stack operation going on to maintain states, the local states of function. That's what stack frames do in most programming language designs, right? So you can see that. Some of you might ask, can I do a queue with Python with a list in Python? You can technically do that, but I recommend not to. For simple use case is fine. I'll cover that a little later when I talk about collections.deck. So though you can implement a queue in Python where you can append to one end of a list, but you pop from the 0th index. That means append, pop of 0, append, pop of 0. We'll implement a queue. The drawback here is that there's a remove complexity, which means that appending is not out easy, adding on top, but removing from bottom will involve the cost of reindexing each elements all over again. So you have that complexity when you're doing queue-like operation. But I would say practically, if you're dealing with a list that's got just about 100, 200,000 items, I think you can still use queues for practically you don't see much performance difference. Only when you have an extremely large data set, you have a list of million elements or 10 million elements or something like that, implementing queue using a list will not be very efficient. There are dedicated data structures for that. It's not part of the Python built-in. Queues are something that's used for building frameworks, producer, consumer algorithms, and so many other things. So it's actually available as a collections module feature called a deck, which I will have a dedicated session on later. So in this session, I think we almost run 1 hour, beyond an hour. So I will end right here. So in this session, I give you the basic concepts of a list. I told you some of the basic list operations you can do. And I covered how many methods. I talked about insert, append, and extend, and pop. 4 methods. We'll continue the part 2 of the session. Next session will be the part 2 of lists, where we'll go much more detailed, more involving in a lot of things you can do with a list. I hope you found this video useful. If you do really like what I'm doing, if you really enjoy the session, and if you really are learning new things in this video, do subscribe and hit the like button. So I would be more encouraged to do more programming videos like these. Thank you very much. So meet you in the next video.